Now we can additively decompose this velocity gradient tensor. Remember, L is the spatial gradient of the spatial velocity. We can additively decompose it into a symmetric part, which we call the stretch rate tensor, and an antisymmetric part, which is called the spin tensor. So this is the spin and this is the stretch rate. So there's a standard way of splitting any tensor into a symmetric and antisymmetric part. The symmetric part is half L plus L transpose. So in indicial notation, Dij is half Lij plus Lji. It's obviously symmetric. And the antisymmetric part of the spin is Wij is L minus L transpose, which is Lij minus Lji. So Wij is equal to minus Wji. This is a skew symmetric tensor and this is a symmetric tensor. Now, what is the significance of the split? What is the significance of the stretch rate and what is the significance of the spin? This is best understood in terms of a problem. So the problem is this. Let us try to find the an expression for L and therefore D and W in terms of the stretch rate U. Remember, F can be polar decomposed into R times U. And now we try to find L in terms of rate of change of U. Let us try to do that. So we'll start from here. And so we will use two expressions. One is F is equal to Ru. This we had learned before. And then just a few slides ago, we derived that F dot is equal to Lf, which means that L is equal to F dot F inverse. Now use this here to use this and this together. So write L as F dot is of course R dot U plus Ru dot, and F inverse is U inverse R inverse. Do the multiplication. You have R dot R inverse plus R U dot U inverse R inverse. Remember, R is proper orthogonal. It's a rotation tensor. So this is R dot R transpose. Inverse is same as transpose plus R So this is your L. Now, it is easy to show that this part is actually skew symmetric. Why? Because we know that R transpose is identity. R inverse and R transpose are the same. So R dot R transpose plus R transpose dot is equal to 0, which tells you that R dot R transpose is equal to minus R transpose dot. But R transpose dot is simply minus of R dot R whole transpose. So this is a skew symmetric tensor. So this part is skew symmetric. So now when we take the symmetric part of L, this part doesn't appear and you get symmetric of R U dot U inverse R transpose equal to D. D is the symmetric part of L. Now, as you can see that if I have a pure rotation in which U is equal to I, in that case U dot is equal to 0 and the symmetric part is 0. So for a situation where there is no stretch, the stretch rate turns out to be 0. Also, this is uh, this is a rotation. R transpose, pre-multiplication by R and post-multiplication by R transpose is a rotation of this particular tensor. And the symmetric part of a rotated tensor is also symmetric, so we can take the R out and write symmetric part of U dot U inverse R transpose as D. This is also equal to 0 if U is equal to the identity tensor. That means if you have a pure rigid body rotation.